Okay, folks, so this thing, small angular approximations, this is something I really like because it links with further maths. Now, if you do further maths AS, you may know about the Maclaurin series, and this is a link to the Maclaurin series. So what we're talking about is this idea of small angular approximations. Essentially what I'm getting at is that sin x, cos x, and tan x, and sec squared, and all these kind of things, any function can be approximated, written a different way, as essentially a polynomial. So a polynomial means something that goes up in powers of x, okay, which is called a power series also, right? So what I'm saying is, with the Maclaurin series, which you don't need to know what the Maclaurin series is, the next slide is going to be, this is what you need to know. But obviously, I really hate the idea of just saying, here's the thing, have no idea where it's come from, okay? And obviously in this video, we're not going to be able to get into where the Maclaurin series comes from. But what's great about the Maclaurin series is that essentially any continuous function within an interval, so i.e. there's no breaks, there's no asymptotes or anything within that interval, and it has to be differentiable everywhere within that interval, can be expressed as this polynomial here. Okay, so what we're going to do is we're going to quickly build one. So I'm going to show you how sin x can be written as a polynomial like this. Okay, so f of x is sin x. This is just quick. You don't need to know how Maclaurin series works, okay? But this is showing you where this is coming from, what I'm about to show in the next slide. So f of x equals sin x, yeah? What this is saying is that f of naught, right? So I'm going to start building up my series. The first term is f of naught. So f of naught is sine replacing the x with naught, so that's nothing, right? So I'll put this over here. So at the moment, sin x can be expressed as nothing, plus, now we've got our next term, f dash of x, but with 0 in there. So first I need to find f dash of x. So sin x differentiates to cos x. I put in 0 then, because that's what it says at the top here. So cos of 0, as we know, is 1. So that's 1 times x. And then we've got the next term, which is f dash dash of 0. So first I need to find f dash dash. So that means differentiate the function again. So cos x goes to minus sin x, yeah? And the f dash dash of 0 then is minus sine of 0, which we know sine of 0 is 0. So at the moment we're on 0, x squared over 2 factorial, that's that term there. And then we've got f dash dash, so f dash 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 of x minus sine x is going to go to minus cos x. And f dash dash of 0 is minus cos of 0, which we know is minus 1. So this is minus, and then that's the 1, x cubed over 3 factorial. Remember, 3 factorial means 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1, you see? And we could do a couple more terms if you want, right? So the fourth differential of x is going to be minus cos x is going to go to minus sin x. So this brings us back to sin x. So of 0 is 0 again, sine of 0 is 0. So at the moment we've got 0, and the pattern is x to the 4 over 4 factorial. And then we've got the fifth differential of x, sine x goes back to cos x, the fifth differential at 0, cos of 0 is 1. So we're back to plus 1 x to the 5 over 5 factorial, okay? So essentially what we're saying is that sin x from the Maclaurin series can be expressed as, where that 0 is, I'm just going to get rid of that. So x minus x cubed over 3 factorial plus nothing, x to the 5 over 5 factorial. So x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial. And it would just keep going. Okay, and I think I'll just quickly show you on autograph why, like how well that fits. It fits really well, okay? I know I shouldn't really be teaching you about the Maclaurin series, but everything we're about to do leads on to this. So y equals sin x, yeah? and we're saying y is the same as x minus, and let's see how we do. So x cubed over 3 factorial, right? So there's the first two terms of that series expansion. You see, x minus x cubed over 3 factorial, and look, it matches quite closely, doesn't it? It's between like minus 1.5 and 1.5, and if I add more terms in, if I add more terms into that, you'll see the approximation gets better and better. X to the 5 over 5 factorial. Oh, look, it's expanded now to like 1.75 minus 1.75. And we just add a few more terms into that, and you'll see how well this fits. Now, the Maclaurin series, 7. Oh no, it's just like watching your granddad type, isn't it? Over 7 factorial, and then plus x to the power of 9 over 9 factorial. Do you see that? So if we keep adding this pattern of plus minus odd powers over odd numbers factorial, this is actually going to match the graph exactly if I could go on forever. And that's something we could prove later, right? But back to the small angle approximation. So now we are back on to your work here. What happens if x is really, really, really small? So if x is 0.01 or 0.0001, or if x is just 1, that's fairly small, isn't it? 1 between 1 and minus 1, or half and minus a half. So when I say x is small, that's very relative, isn't it, to kind of what level of accuracy you're looking for. Okay, and so for your exams, think about it. If I've got x is really small, so x, let's say x is 0.01. 0.01 to the power of 3 is absolutely tiny, isn't it? It's going to be 6 decimal places. So x cubed is going to be 0.00001. Do you see? And x to the 5 is going to be even smaller, right? And if I picked x to be 0.0001, it's the original value, and then I cubed that, then you're going to get 12 decimal places. So the point is that the big powers of x just become negligible. You don't need that much accuracy depending on the situation you're going for. So all these terms can basically be ignored when x is small. So we're saying as x tends to 0, i.e. it's small, sine x tends, well actually I'm gonna change this round. So we're not saying that yet. We're saying when x is small, sine x is approximately equal to x. Can you see? Okay, and we'll talk about the as it tends to 0 in a bit. Okay. Now cos x, from the Maclaurin expansion, same thing as what I did in the previous slide. You'll end up with 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, etc. Okay? Now again, when x is small, it all depends on what accuracy you're looking for. So Edexcel have decided that anything above x cubed can, anything x cubed and above can basically be ignored. Okay, so they're saying when x is small, x squared will keep that one, but x to the 4 and x to the 6, that's just too small. So we're going to ignore it. Okay, so we're saying that cos x is approximately equal to 1 minus x squared over 2, right? Which is the same as 2 factorial. So 1 minus x squared over 2, okay? These things you absolutely have to remember, and also tan as well. Tan is deemed to be from Maclaurin series. You could do exactly the same thing as what I just did, and you cancel out all of your big powers of x again, and you'll end up with tan x is approximately equal to x, okay? So again, looking at the graph, how accurate are we talking about? So let's look at the cos graph, for instance. This is the cos graph here. And if I'm saying that y equals 1 take x squared divided by 2, it's my approximation for cos, you can see actually it's quite good. If I zoom in, it's quite good between 0.5 and minus 0.5. So that's what I'm talking about, these approximations, why they're useful. because this curve, cos x, which can be quite nasty to work with, has now just been reduced to 1 minus x squared over 2, this really nice quadratic. And between minus 0.5 and 0.5, it's actually fairly accurate. Okay? So that's what we're working with. These are the three things that you really need to remember. And how can we use this then? So I also just want you to note, so what we're saying is sine x is approximately equal to x, so is tan x. So the way to remember it, sine and tan, both approximately equal to x. Cos x is our 1 minus x squared over 2, okay? Now, things to note here, that if we have sine 4x, just like with the Maclaurin series, if I made it from scratch, I would just replace x by 4x, okay? So sine 4x would approximately be equal to 4x, you see? Just like our f of x stuff, if I put f of 4x. So cos 5x would be approximately equal to 1 take, and be careful here, you're only replacing the x, 5x squared over 2, which is 1 minus 25x squared over 2. Can you see? You have to square everything in there. That's the thing to be really careful of, okay? So it says when theta is small, find the approximate value of this. This is the kind of question that you're going to get set. So sine 2 theta plus tan theta over 2 theta. So when theta small, this thing is going to be approximately equal to, well, sine 2 theta is 2 theta. Tan theta is just theta over the denominator, which is 2 theta. So at the moment I've got 3 theta over 2 theta. So this thing is approximately equal to 3 over 2. Okay? So the approximate carries over here. Likewise here, I've got 1 minus cos 2 theta over tan 2 theta sine theta. So this is approximately always right when theta is small. Okay? That's important to put that down. So I've got 1 minus, and then cos 2 theta is 1 take 2 theta all squared divided by 2 over tan 2 theta, which is 2 theta, and sine theta, which is just theta. You see how familiar you need to be with these three things here, okay? So the 1 minus 1, that goes, and I've got a minus, minus, so that's plus, okay? And I've got 2 theta on the top all squared, so that's 4 theta squared over 2 on the top. And on the bottom, I've got 2 theta times theta, so that's 2 theta squared. So 4 over 2 theta squared is just 2 theta squared over 2 theta squared, which is 1. So I'm saying that this thing is approximately equal to 1. Can you see? When theta is small. Now, a bit more of a formal example then. I really like this, actually. I didn't think I would, but I do really like it. So, 3a, find cos of 0.244 rad. And it's just asking me to put this in it. So this is like an exam question. It's asking me to put it in my calculator and say what the answer is to 6dp. So, okay, cos, make sure your calculator is in radians. So cos of 0.244, I get 0.970379, and that's to 60p. Okay, cool. It says use the approximation for cos to find the approximate value for the same thing. So cos 0.244 is approximately equal to, remember, 1 minus x squared over 2. So 1 minus x squared over 2, which is the same as, so 0.244 squared divided by 2, 1 minus that answer, 0.970232. So pretty close. That's the real one, but remember your calculator is actually just using an infinite Maclaurin series. So your calculator is also an approximation you need to remember, but a better approximation than what we've got because it's got a lot more terms in it. Okay, calculate the percentage error in your approximation. So how do we calculate percentage error? Again, another thing that you may already know, but you do need to have a strict formula for this. So we're going to write approx. So your formula is approx minus exact over the exact times by 100. Because this is your difference, isn't it? Your percentage difference. And if your approximation, it tells you if it's lower or higher. If your approximation is less than the exact, then you're going to get a negative, which means you are you're underestimating, do you see? Or if your approx is higher, you're going to get a positive value, so therefore you're overestimating. And timesing it by 100 obviously makes it a percentage. So my approximation is 0.970232 minus my exact. No, it's not actually exact. All over my exact, so 0.970379, and then we'll times the whole thing by 100. So if I put that in, I should get 0.970232, take 0.970379 divided by 0.970379 times by 100. So I should get minus 0.015%. Okay, so there's your percentage error. Okay, part D. Calculate the percentage error in the approximation for cos 0.75 rad. So it wants us to do the same thing as we just did, but it's not giving us any help this time. So the exact, right, cos 0.75, and this is going to be interesting because I wonder if you know what's going to happen now. So cos 0.75 on your calculator, that's 0.731688, but let's do it to 60p again, so make that 9, right? And then our approximate cos, 0.75 is approximately 1 minus that x squared over 2 factorial, so 2. So 0.75 squared divided by 2, 1 minus answer, and I get 0.71875. So percentage error, we know, is approx minus exact over exact times 100. So approx minus exact over exact times by 100. So this is, what's that? There's your approx. So approx take away 0.731689 over the answer times by 100. So this is minus 1.80%. Okay. So part E says explain the difference between your answers C and D. Can you explain that? Like, really, what are we getting at here? We're saying that the error is actually, I know we're talking about really small numbers, but that's a massive difference in error, isn't it? This one here is 100 times bigger, at least, than this error here, just because we picked, well, why is that? Well, look at the graph again. Look at the graph. Where's 0.244 radians? 0.24 radians is like here. So the graph matches really well. But if you look at 0.75, you're here, and you can see that there's a disparity between your graph and the original graph. Okay? So that's how to answer that question. The final one here. This is so important now. All right? How's the video for time? Oh, 18 minutes. Okay. How to use, please stay with me for this. So how to use differentiation from first principles to prove that sine differentiates to cos. This is the one you need to know for your exam, not the fancy one I made for you if you watch that as optional, the official one. This is the exam one that you must know, okay? So I'm going to differentiate sine to cos, right? So f of x is sine x. So I'm going to do this fairly quickly because I know the video is getting long. So we know from first principles that f dash of x is the limit as h or delta x, whatever you want, of f of x plus h minus f of x over h. Okay? So we're going to apply this now. So the limit as h tends to 0 of f of x plus h. So we know f of x plus h is sine x plus h. So sine x plus h, take away f of x, so that's take away sine x over h. Now, hopefully you're screaming out at the screens, oh, that looks like sine a plus b, and that's exactly what we want. Sine a plus b, fantastic. So there's our cos x sine h. So this is why we did this in this time of the year, because you didn't know the addition formula. Okay? Right, so what do we have now? So we've got limit as h tends to 0. So I'm going to factorize, I'm going to put together this stuff. So sine x cos h takes sine x all over h, so that's this and this, yeah? Plus, separately, cos x sine h over h, that's this and this and this, okay? So this is all in the limit. Now, can you see I can take out a factor of sine x here? And sine x has nothing to do with h, so that's why I can put it on the outside. So on the inside I've got cos h, right? Cos h, take away 1. You see, if I take out the sign in there and the sign in there, and it's still over h, plus the limit, because now we're taking the two limits separately. And again, that cos x can go on the outside. There's a cos x here, which has nothing to do with h. So cos x, limit, h tends to 0, of sine h over h. Now we know h is small in this situation. We haven't actually made h 0 yet. We just know h is small. And therefore we can convert our cos h into 1 minus h squared over 2 minus 1 over h plus cos x, limit as h tends to 0. We know that sine h, when h is small, is just h. So we get h over h. So here we've got sine x, limit, h tends to 0. So I've got 1 take 1, that's gone, and minus h squared over 2 divided by h. So that's minus h over 2. Can you see? The 1's cancel, and this h divides this h squared here. Plus cos x, limit. Remember, we still haven't taken the limit yet because you have to take it all at the same time. H over h is 1. Right, now we're in the good position. Remember, we're saying that h is small, but we haven't yet said that h is 0 or tends to 0. So our final line, I'm going to take the limit now. So I've got sine x here. As h tends to 0, I've got minus 0 over 2. So that's just 0, do you see? Plus cos x. H tends to 0 of 1. Well, as h goes to 0, 1 is unaffected, so that's just 1. So can you see this disappears, and you're just left with cos x. Yay! So that's how we would use small angle approximation to differentiate sine to cos. In class, you're going to do cos to sine. I might even get you to do tan as well. But now you can differentiate this from first principles using your small angle approximation. Really powerful stuff. Again, if you're not sure about that, just watch that little bit again, this last slide again. All right.